Now in this case study again, we start with chemical composition and you got material properties, but you always are shown because the chemical composition is a continuous data, but then we make it discrete because ultimately we are looking at different levels, and therefore we can compare that with furnaces and operator shift and different process parameters. In the handouts that I've given you has a different list of measurable parameters and responses for a variety of processes. And before our brainstorming session, we will reflect on those as a starting point. Now here objective was to optimize chemistry for high toughness and high strength. And what you will find that the chemistry that you use to increase UTS and yield strength is exactly opposite to what you need for toughness. And therefore we sort of do juggling. Now there is no one optimal solution, but it is we just give an indication of how you can compromise on both objectives. And we got these mechanical properties for 35 heats. The advantage of putting these reports into Excel format, because when you got multiple responses, the penalty matrix visualization becomes slightly difficult because it is ultimately a penalty matrix for one response. And then you need penalty matrix for the second response, and it gets a bit hard. So what we need are Excel sheets where you can sort by factor name. And therefore you can see the impact of aluminum on UTS and yield strength. Or you can see the impact of carbon on CVN, which is a measure of toughness, as well as UTS. So once you do sorting, you can sort them according to input files, according to responses, according to the sensitivity study to your threshold values, or you can sort them according to factor names. And you can also put a filter on the strength of those values, the strength of factor values as well. Now, interaction sheet, we say that you sort them according to factor names, then according to levels, and then according to the second factor to which this factor interacts. And once you do that, you will get analysis across responses. Because what we want to do is we want to study impact of aluminum. For example, aluminum is okay because it only influences UTS and yield strength, but it is consistent, bottom 50% are optimal for both, and that variation is not sensitive to toughness. And therefore, we can choose aluminum into bottom 50% for that particular steel in the confirmation trial plan. But we've got a problem with carbon. Carbon bottom 50% is optimal for toughness with not very strong, but it's got two interactions and the strength of interaction is high. But carbon 50% is bad for UTS. So you need high carbon to increase UTS. And then you got actual range as well. So it is not just domain knowledge with the train, but actually the range which works for your foundry. But now there is a conflict between carbon. Similarly, chromium, there is a problem that bottom 50% is avoid for toughness and top 50% is optimal for yield strength. So again, there is an issue. So how do we choose which one to pick up? And then you need domain knowledge for that. But at least we got this ranking with our ability to sort. And then if you are in doubt, you look at the penalty matrix, whether to pick that up in the confirmation trial plan or not. So what we are doing now, we are gaining deeper insight. We are creating hypotheses based on evidence with this penalty matrices. And then we sort many effects and interactions which are available into these Excel sheets. Now, as I've said before, you can combine one or more penalty matrix reports from different files and sort columns to study the influence of factor settings. So if you've done some study last year and you've done some study today, then the library of these reports create new knowledge and retain your knowledge. And that will help you to see how your process has improved or gone down. Or if you have 3 foundries in 3 different locations, you can combine those penalty matrix report sheet and then see the variation across 3 foundries in 3 different locations and develop that evidence. And that is how you do the sorting also, which we have done in this case, to understand the influence of one factor onto multiple responses. Or sometimes you have to do parametric study on penalty values. And again, you can do that and you do the sorting again to see. And that's where you need quiet 1 hour and hopefully before your quality control meeting, so that you give those options with justification and present those reports to all the members of the meeting. So what we again say that you need to use minimum number of correlated responses in one analysis. So try not to have all 10 defects, because it will be then much harder to create a proper confirmation trial plan. So try to be specific. Just have a couple of responses which really matter for your analysis. Again, now there are a couple of situations, because now you got these conflicting responses. So the first situation is you have consistent optimal and avoid levels across responses. Life is simple. If that happens, that factor should go to confirmation trial immediately, even if the strength is low. For example, in case of aluminum, it is so consistent that the bottom middle 50% is optimal, so lowering aluminum is good. But lowering means that is a trend, but you are getting exact ranges here, which is specific your foundry. And this is the variation of aluminum between 0.063 to 0.099. Similarly, you can get, for example, carbon drop for UTS and yield strength. Top 25% is bad, bottom 50%, middle 50% is good. So the conclusion is carbon drop should be into the bottom 75%. That is, avoid top 25% carbon drop. And then you are sort of okay, because then you will be supporting UTS. You try to increase UTS. Again, you get a particular range for that, which is specific for your company and your product. Now the problem comes where you have contradicting and equally strong responses. And this is where we would really like to work on your data set but we'll complete this case study for the sake of clarity. But this is where we like to work on your data set, which is again real. Now in this case, we've seen this chromium. They are very weak main effect strength, but they interact. And the strength of interaction is strong. So you either ignore chromium and do nothing, or you choose to support either toughness, or you choose to support yield strength. So this is where you get into problem. And then what we are suggesting is then look at your interactions sheet. Because there's one interaction here, look at the interaction sheet. And then look at a decision that you already made. Now in case of chromium, for yield strength, you find that this chromium interacts with one parameter, which happens to be aluminum. And you already made a decision that aluminum should be in bottom 50%. So because you made a decision aluminum in bottom 50%, and if this is in bottom 50% and chromium is in top 50%, then it's an optimal interaction. So support aluminum. And therefore you can make a decision of supporting aluminum, and therefore you said, okay, toughness, you compromise, but then pick up chromium to support high yield strength. And then we'll worry about toughness later on. We'll pick up other chemistry which will support toughness. But this is a small change which will then help us to engage into positive interaction. Now we need domain knowledge. That why aluminum and chromium, when they come together, what happens in the metallurgical science to give you high strength. And this is where you need that literature review. Now, you come up with this carbon equivalent, which is what we want to sort of achieve or maintain. But then this formula has got, and this is where you will find lots of ratios and chemistry parameters or combinations of different parameters to maintain a particular factor. In this case, it's carbon equivalent. But this is where you need domain knowledge from textbooks, etc. But what we are saying that, okay, you got carbon, manganese, chromium, molybdenum, and then you get different alloys. Now, we already made a decision on chromium. We already made of course, aluminum is not here, but we made a decision on chromium. we got to make decisions on carbon, manganese, and other factors as well. Now, what we do now is contradicting and equally strong levels, and we look at carbon. Now, the problem with carbon is top 50 is good for UTS, but bottom 50 is good for toughness. So what do? Now, we had aluminum and chromium, which supported UTS. So what we say that, okay, let's look at interactions, because here, top 50 does not interact, there is no optimal interactions, but bottom 50 has interactions which are bad. And if I put toughness, then there are two interactions which are good. So now when you make a decision, you have to now need a real quiet thinking with this domain knowledge, where you look at all interaction penalty matrices. And then what we say that, okay, for carbon, there are these two interactions, which happens to be this in the interaction penalty matrix sheet. And the carbon with UTS is avoid, and there are these two interactions. Now, these avoid interactions are with MnS ratio, manganese sulfur ratio, and then this is with sulfur, percentage sulfur ratio. And these are avoid. So if you got carbon in bottom 50% and manganese sulfur ratio is in top 50%, then it is bad. There are 8 castings with 100 penalty values and none with 0 penalty values. So again, it needs to be cross-checked, but you got this evidence from your data sheets. Similarly, you get carbon with manganese. Manganese you want to be in bottom 50%, and argon stir it should be in middle 50%. Reduce the squeeze. But now you see the trend. You see the trend here that manganese you want it to be low, and sulfur, if you keep it high, automatically manganese to sulfur ratio would be low, because manganese is low, sulfur is high, and this ratio is low. So even if you decide to choose carbon to support toughness, but then keep MnS ratio into high, that is not in the bottom 50%, but also into, MnS ratio not in top 50%, but in the bottom 50% region. That is not F2, which is in this region. Then instead of 8, you got only few, but then there are a number of casting which are good. And then again here, you say that, okay, sulfur, I keep it on the larger range, that is top 50%, which is F2 naught, which is here, and then the statistic is not bad. So what we do, this MN ratio, we choose to nullify or mitigate these interactions, and therefore this top 50% MNS ratio is chosen as bottom 50% as an optimal in confirmation trial plan. So that interaction, we mitigated those effect of that bad interaction. And similarly, carbon, we are supporting toughness with our carbon, and therefore we are keeping argon stir mix in middle 50 to support this positive interaction for toughness. We are keeping manganese into bottom 50% to support toughness, and then we choose this MNS ratio and the sulfur ratio into opposite ranges, and therefore highlight those into main effect sheet. So they become candidate for your confirmation trial plan. So this decision can be done by process engineers once they know how to do it and justify their decisions, and then present that information into quality control meetings. Similarly, carbon equivalent and copper. We got these interactions, but then we get a problem with this interaction because of the choices that we have made on copper. And therefore, then sometimes ignore some of the interactions because we can't adopt everything. But again, okay, we're keeping these two parameters low, which has got significant impact on carbon equivalent, but then we look at the interactions as well, which will minimize those defects. And then we chose copper and chromium to increase this along with aluminum and other composition because they conflict with each other anyway. So we then decided to tweak those processes and then come up with this confirmation trial plan. So in order to optimize this conflicting mechanical properties, you're changing so many parameters along with their ranges with justification. This is what we would like to demonstrate. From your data set where you have 70 parameters, you come down to these 5, but not using filters, which are statistical filters, which are used in statistical packages. We are using penalty matrices and domain knowledge to come up with those ranges.